Close your eyes for just a moment and imagine floating through the infinite darkness of space. No sound, no gravity pulling you down, just endless quiet and the soft glow of distant stars scattered across the velvet night like diamonds on black silk. Now open your eyes again, because tonight we are going on a journey together. A journey through the most peaceful, most fascinating, and most soothing corners of the universe. We are going to drift slowly through solar systems you have never seen, worlds you have never imagined, and discover the gentle rhythms that govern the cosmos. This is not a race. This is a meditation, a chance to let your mind wander among planets that spin in perfect harmony, stars that burn with ancient patience, and moons that circle their worlds like dancers in an eternal ballet. So settle in, get comfortable, let your shoulders drop and your breathing slow, because for the next hour or so, we are leaving Earth behind and drifting into the magnificent, tranquil beauty of solar systems beyond our own. Before we begin this cosmic journey together, if you are finding peace in these words and images, I would be so grateful if you would take just a moment to like this video and subscribe to the channel. It helps more people find this quiet space we are creating together, one sleepy soul at a time. Your support means the universe to me. And now, let us drift into the stars. Imagine a world where every evening, two sunsets paint the sky. Not one, but two brilliant orbs sinking toward opposite horizons, casting double shadows across alien landscapes. This is not fantasy. This is the reality of circumbinary planets, worlds that orbit not one star, but two, threading their path through the combined gravity of twin suns. These planets move through space like needles weaving through fabric, their orbits shaped not into simple circles, but into elegant braided ribbons that loop around both stars at once. The mathematics of their motion is complex, yet nature finds stability even in this cosmic dance. When conditions are just right, when distances and masses fall within certain ranges, gravity settles into repeating rhythms that can last for billions of years. Standing on the surface of such a world, you would watch the sky transform in ways Earth could never show you. Sometimes, both suns would hang in the sky together, blazing with combined warmth. Other times, they would eclipse one another, and shadows would shift and merge as one sun passed in front of the other. Seasons on these worlds are unlike anything we know, driven not by axial tilt, but by the ever-changing dance of stellar partners that drift apart and draw close again in their own orbits around each other. Studies of planet formation suggest that even in the chaotic push and pull of a binary system, dust and ice can still gather into solid worlds. Growth may pause when spiral waves sweep through the protoplanetary disk, and resume when the turbulence settles. It is a testament to nature's flexibility, to the way matter finds pockets of order wherever physics allows. These binary worlds widen the stage for potential climates and atmospheres we have never witnessed. They expand the possibilities for where life might arise, showing us that the universe does not limit itself to single-star systems like our own. Now let your mind drift to another strange reality. There are solar systems out there where planets orbit in the opposite direction from their stars' spin. These retrograde worlds move backward through space, as if rewinding the cosmic clock. Most planets follow the rotation of the disk from which they formed, spinning in the same direction their star spins, like children following the current of a gentle river. But retrograde planets swim upstream. They may have been flipped by a gravitational encounter with a passing companion, torqued by a skewed disk during formation, or jostled in the violent scuffles of a young solar system where planets had not yet settled into stable homes. The result is an orbit tilted at a sharp angle to the stellar equator, sometimes by just a little, sometimes by a lot, and occasionally completely reversed, looping above and below the star's poles. This geometry reshapes everything about the planet. Weather patterns become strange and unpredictable because the direction of day and the direction of the year tug in opposite directions. Tides behave differently. Atmospheric currents swirl in ways that would never happen on a world where orbit and rotation are aligned. Each retrograde planet is like a scar on the face of a solar system, preserving clues about ancient collisions or distant wanderers that once passed too close. By reading these tilted paths, astronomers can reconstruct dramas that played out billions of years ago, events that ordinary, well-behaved orbits would hide forever. It is detective work on a cosmic scale, and every backward world is a case file waiting to be solved. Let us pause here and consider something deeply comforting. Surveys of distant starlight have revealed a quiet abundance that changes everything we thought about our place in the universe. Roughly 1 in every 5 sun-like stars appears to host at least one planet near the size of Earth. When researchers correct for the limitations of our instruments and the angles from which we observe, a striking pattern emerges. Small worlds are everywhere. Many of them lie in or near the temperate zones where liquid water could exist under the right atmospheric conditions. This does not guarantee oceans or breathable air or forests filled with life, but it transforms the search for habitable worlds from a desperate hunt for rare jewels into a methodical cataloging of nearby possibilities. Every transit measured, every tiny wobble in starlight mapped brings forward another candidate world for deeper study. Future telescopes, more sensitive than anything we have today, will sift through the atmospheres of these planets, searching for the shimmer of water vapor, the signature of oxygen, the hints of methane or carbon dioxide that suggest active weather systems. The implication is profound and strangely soothing. The night sky is not a barren desert. It is punctuated by countless small shores, rocky worlds waiting quietly for us to learn their weather patterns, their geology, their stories. We are not alone in being small and rocky. We are part of a vast family. Now imagine the loneliest existence a planet could endure. Set adrift by gravitational encounters or never bound to a star in the first place, rogue planets wander the interstellar dark. They have no sun to warm them, no light to paint their skies. They move through space lit only by starlight from afar, faint and cold, and warmed only by their own internal heat, the fading memory of their formation, and the slow decay of radioactive elements deep in their cores. Their skies hold eternal night. No sunrise will ever break across their horizons. No seasons will ever change. And yet, they may not be entirely lifeless. Some rogue planets might carry thick, insulating atmospheres that trap what little warmth they have. Others may harbor buried oceans beneath kilometers of ice, kept liquid by tidal stirring during rare close flybys of other bodies, or by the steady pulse of internal heat. Detecting these drifters is extraordinarily difficult because they do not silhouette a parent star. But careful surveys can catch their faint glow in infrared wavelengths, or the fleeting brightening they cause when their mass bends the light of a distant star. Their existence tells us that planetary birth and eviction are common outcomes of crowded young systems where too many worlds compete for too few stable orbits. These lonely wanderers turn interstellar space into a subtle archipelago, a scattered fleet of cold islands drifting silently between the lamps of the galaxy. Let time stretch backward now, far beyond the memory of humanity, beyond even the formation of Earth. Astronomers have detected solar systems that are almost as old as the universe itself. Some stars formed when the galaxy was still young, enriched by only the first few generations of stellar explosions. Around these ancient suns, we have found the fingerprints of planets. Their chemistry is sparse in heavy elements compared to modern stars, yet still sufficient for dust to clump and worlds to build. These venerable systems have quietly orbited for billions upon billions of years, surviving cosmic mergers, tidal shuffles, and waves of new star birth. If their planets still possess atmospheres, those skies have weathered epochs beyond any saga told on Earth. Time has had a chance to test every possible climate, every chemical reaction, every geological cycle. These systems are time capsules, preserving an early recipe for planet formation that challenges models built from studying only our local neighborhood. They connect the first chapters of cosmic history with the planetary diversity we see today, proving that world-making began soon after the first stars ignited and has been humming along ever since, patient and persistent, shaping matter into spheres wherever gravity allows. Worlds do not always stay where they first took shape. Migration is one of the most soothing and yet transformative processes in planetary science. As young planets exchange momentum with the gas and dust of their birth disks, they can drift inward or outward, sometimes drastically. An icy giant born in the frozen outskirts might slowly spiral toward its star, becoming a hot Jupiter in a place where such a massive world could never have formed. Later, after the gas clears and the disk fades, gravity games continue. Planets tug on one another, trading energy and angular momentum until their orbits stretch, shrink, or even swap places. This slow reshuffling can move a frozen world into a warmer realm, or park a giant planet close enough to its star to reshape the climate of every neighbor. Migration sculpts resonances, clears belts of debris, and can trigger showers of comets that deliver water and organic molecules to inner worlds. It explains why so many systems defy the simple inside rocky, outside icy pattern we see in our own solar system. Planetary systems are living architectures, molded by friction and gravity, with final layouts that remember the currents and encounters of their youth, long after the original disk has vanished into starlight and silence. Picture now a solar system far more crowded than ours. Compact families pack several planets inside an orbit smaller than Mercury's, each world circling its star in mere days or weeks. Their spacing is tight yet stable, like pearls strung on nested threads. Because the planets formed together and settled into balanced configurations, they do not collide or scatter. In such places, neighboring worlds loom large in each other's skies. A moon seen from Earth is a distant glowing circle, but on these clouded worlds, a neighboring planet might fill half the sky, waxing from a bright disk to a slender crescent within a single week. Close quarters amplified tides, stir atmospheres, and create rhythms where planetary conjunctions repeat like the steady beat of a metronome. Crowding does not mean chaos. If masses and distances fall into harmonious ratios, these systems can survive for eons without catastrophe. They reveal that nature often prefers efficiency, building many medium worlds rather than a few giants, and spreading them across snug lanes where gravity holds them in delicate balance. Their climates and compositions may vary dramatically from world to world despite sharing the same star, offering laboratories where a single sun feeds a bouquet of planetary experiments arranged almost shoulder to shoulder. Not every solar system follows the familiar pattern of rocky planets near the star and gas giants farther out. Some form with no rocky planets at all. If a disk is poor in heavy elements, or if giant worlds form early and consume most of the available material, the inner regions may never assemble durable rock and metal cores. Instead, gas and ice dominate, yielding a family of mini Neptunes or gas giants with only small solid centers. In such systems, heat from the star sculpts puffy atmospheres, while distant cold preserves rings and moons carved from icy debris. The absence of terrestrial surfaces transforms everything about potential habitability and geology. There are no continents to drift, no volcanoes to recycle crust, no shorelines to cradle oceans under open sky. Yet chemistry still thrives in clouds and on the surfaces of moons. Magnetic fields can shield deep atmospheres from stellar storms. These rockless families demonstrate that planet formation is not obligated to produce Earth analogs. The universe experiments freely with ensembles where air and ice are the main stage, while stone plays only a hidden supporting role deep beneath layers of gas. There are solar systems where planets orbit in perfect harmony. Resonant chains lock worlds into synchronized motion, where for every set number of orbits completed by one planet, a neighbor completes another exact count: 3 to 2, 4 to 1, 7 to 3. This clockwork arrangement keeps orbits from crossing and can persist for immense spans if no large disturbance arrives. The pattern often forms as planets migrate slowly through the disk, capturing one another into step, like dancers adjusting to a shared rhythm. Harmony leaves fingerprints in the precise timing of transits and the subtle tugs planets exchange, allowing astronomers to weigh them and probe their internal structures. For any inhabitants, if such exist, the heavens would present regular meetings of bright companions, spaced predictably like notes in a repeating melody. Such systems show that gravity, when given time and gentle friction, can compose stable music from dust and gas. The result is not rigid but resilient, a natural cadence that reveals the history of migration written into the beat of the years. It is one of the most peaceful concepts in astrophysics, this idea that chaos can settle into song. In our solar system, planets vary wildly in size. Tiny Mercury, enormous Jupiter, but elsewhere the story can look very different. Several observed systems contain planets that are all unexpectedly close in size, as though stamped from the same cosmic mold. These worlds usually fall between Earth and Neptune in diameter, forming neat families of super-Earths or mini-Neptunes lined up in tight orbits. Their surfaces and atmospheres can still differ wildly depending on distance from the star, the chemistry of the original disk, and the histories of collision and migration. But their uniformity in size suggest formation conditions that distributed material more evenly, or gravitational interactions that kept competing worlds in check. Such systems challenge our sense of what is normal. Instead of a few giants and a few small ones, the universe may sometimes prefer symmetry, creating balanced ensembles where no single world dominates the gravitational landscape. These evenly matched systems open questions about whether life-bearing stability might be more common when planets share similar masses and influence, creating a cosmic democracy rather than a hierarchy. There are planets that skim so close to their stars that metal can vaporize. Some race around their suns at distances so short that a full year lasts only hours or days, and daytime temperatures soar high enough to turn iron, silicates, and other minerals into gas. On these ultra-hot worlds, rocky mountains might never form because the ingredients for stone sublime directly into atmosphere. Winds whip metal vapor from the blazing day side to the frozen night side, where it condenses into glittering clouds that might rain molten droplets back toward the scorched surface. These extreme environments reveal the outer limits of planetary survival under fierce stellar radiation. They teach us how atmospheres behave when chemistry is pushed far from familiar ranges, creating exotic weather cycles with no counterpart on Earth. The existence of such worlds shows that planet formation does not avoid the furnace. It adapts, building strange spheres that endure in places we once thought entirely hostile to solid matter. Even in fire, gravity finds a way. A planet's birthplace is not always its final address. Far from a star, in the cold outskirts of a young disk, ices and dust can clump more easily, building hefty cores that later drift inward like rafts on a river of gas. This slow migration happens through drag from the disk itself or gravitational nudges from neighboring worlds. A giant planet born in frigid darkness might eventually settle close to the star, becoming a hot Jupiter that could never have formed in its current scorching location. This inward journey reshapes the architecture of the entire system, potentially sweeping aside smaller worlds or stirring belts of debris into chaotic showers. The traveler can also trigger resonances that lock other planets into synchronized paths. By tracing these migratory footprints, researchers decode the hidden past of systems that appear static today. Planetary placement is a snapshot, not a birth certificate, and many worlds carry beneath their clouds the memory of a long inward voyage across the silent dark. When a massive star reaches the end of its life, it can explode with brilliance that outshines entire galaxies for a brief, terrible moment. This detonation, a supernova, unleashes shockwaves powerful enough to tear nearby planets apart, vaporize atmospheres in an instant, and hurl debris into interstellar space at incredible speeds. Even worlds not directly shattered may be sterilized by the flood of radiation, their chemistry rewritten, their surfaces melted or frozen depending on their distance. The blast carves expanding bubbles through surrounding gas, triggering new star and planet formation in distant regions, while ending it abruptly in the star's own neighborhood. Some planetary fragments might survive as orphaned asteroids or molten cores wandering the void without a sun. Studying these cataclysmic endings offers glimpses into the recycling of cosmic material, since the heavy elements forged in the dying star will eventually seed new systems. Solar systems are not eternal. They are chapters in a cycle of creation and destruction written across the galaxy, each one temporary, each one precious for its brief moment of order. Rings are not just for Saturn. Some exoplanets boast ring systems so vast their total diameter would dwarf even a medium-sized star. These colossal structures may form from shattered moons, captured comets, or leftover debris that never coalesced into companions. When the planet transits its star, the rings block light long before and after the planet itself passes, creating peculiar dips in brightness that first alerted astronomers to their astonishing scale. The sheer size of these rings challenges models of stability because such wide disks must resist collapse, spreading, or evaporation over millions of years. Their presence hints at dynamic recent histories, perhaps involving tidal breakups or colossal impacts. If a moon forms within such a ring, it may eventually clear a lane and grow into a full companion. These oversized halos remind us that even familiar features can reach breathtaking proportions when gravity and time have the right raw materials to work with. Moons are not always minor companions relegated to the shadows of their planets. In some distant systems, a satellite can rival or exceed Earth in size, orbiting a giant planet like a world in its own right. These massive exomoons may harbor atmospheres, oceans, and complex geology powered by tidal heating from both the planet and the star. Their day length depends on the delicate balance of orbital motion and rotation, creating unusual cycles of light and shadow. Detecting such moons is extraordinarily challenging because their signals blend with those of their host planets. But subtle timing shifts and tiny flickers of starlight offer tantalizing clues. If confirmed, these giants would expand the concept of habitable zones to include not just planets, but their satellites as well. A moon with Earth-like mass and liquid water could thrive under the protective magnetosphere of a parent planet, benefiting from both direct stellar light and light reflected from the giant world it circles. The discovery of such a place would redefine where we look for life and how we imagine homes beyond Earth. Some planets roam their orbits utterly alone, without even a small captured rock to accompany them. The absence of moons can result from violent pasts where collisions ejected or destroyed early satellites, or from quiet births in regions of the disk too barren to build them. Without moons, a planet's axial tilt may wobble more dramatically through time, leading to erratic seasons and unpredictable climate swings. Tides are gentler, reshaping coastlines more slowly and reducing tidal heating that can fuel geological activity. The night sky appears stark and empty, with no secondary light to soften the darkness. Yet the solitude of these planets offers a pristine laboratory for studying internal dynamics without the complicating tug of a companion. Their very emptiness poses questions about the ingredients and processes that favor moon-making. In the great variety of solar systems, even a missing moon tells a story about chance, collision, and cosmic scarcity. In rare and fascinating cases, a moon may actually predate the planet it orbits. Born as an independent body in the protoplanetary disk or captured from passing debris, these ancient satellites existed before their host world finished assembling. Later, as material gathered into the planet, gravity pulled the older object into a stable orbit, turning a former wanderer into a companion. Such ancient moons carry chemical and isotopic signatures that differ from their host planets, preserving records of earlier conditions in the disk. Their craters and surface layers might reveal impacts and radiation exposure from eras the planet never experienced. This reversal of roles blurs the traditional line between planet and moon, showing that order in a solar system is often a matter of timing and capture, rather than strict hierarchy. Studying these mismatched pairs deepens our understanding of how bodies exchange places in the cosmic dance, and how early formation stages can overlap in surprising and beautiful ways. In some distant systems, a planet can complete a full orbit in less time than it takes Earth to experience a single sunrise and sunset. These ultra-short period planets are locked so close to their stars that they race around in a frantic loop, sometimes in fewer than 10 Earth hours. Their motion is controlled by extreme gravity and blazing heat, leading to atmospheres that boil away or shift constantly between vapor and plasma. Tidal forces stretch and squeeze them relentlessly, creating internal friction that can melt rock and drive furious volcanic activity. If one could stand on such a surface, the star would fill half the sky, and the speed of the orbit would cause dramatic shifts in light across the landscape within minutes. Though the planet often remains tidally locked, with one perpetual dayside and one endless nightside, these blisteringly fast worlds challenge every expectation about orbital stability and show just how far the universe is willing to push the boundaries of what a planet can endure while still remaining intact. Some worlds beyond our solar system appear to be made almost entirely of water, existing as global oceans without continents or visible land masses. Their dense, pressurized layers may transition from liquid water into exotic forms of ice unseen on Earth, such as Ice 7 or Ice 10, where water molecules crystallize in complex cages under unimaginable pressure. Above this watery interior lies an atmosphere filled with steam or vapor, possibly enveloped by thick clouds that reflect much of the star's light, giving the planet a pale blue halo when observed from afar. These water worlds may experience constant storms, with winds crossing oceans thousands of kilometers wide without interruption. The idea that a planet can form and survive without a significant rocky crust expands our definition of habitability. If life evolved there, it might have no concept of land at all, thriving instead in vast underwater ecosystems, completely alien to anything humanity has imagined, where tectonics and volcanism happen beneath kilometers of crushing sea. Some planetary bodies have been detected with densities and compositions that suggest they are extraordinarily rich in carbon. And under the right temperature and pressure, carbon crystallizes as diamond. These so-called diamond worlds likely formed around stars that were themselves composed of carbon-rich material, allowing carbon to dominate the early planetary disks. As these planets cooled and compressed over billions of years, their interiors may have transformed into vast layers of solid diamond, capped by molten carbon oceans or carbon dioxide-rich atmospheres. Temperatures on the surface might be sweltering or freezing, depending on distance from the star. But deep below, a glittering mantle of crystalline carbon could extend for thousands of kilometers. Such worlds could contain more diamond than has ever existed in the entire history of Earth, turning the concept of treasure into something cosmic and incomprehensible. They remind us that beauty, value, and geology take on unimaginable forms across the galaxy, where universal laws of chemistry and physics produce outcomes that are anything but ordinary. In several star systems, astronomers have found planets so close to their host stars that their orbital periods are measured in mere hours. They complete entire revolutions in the time it takes most of us to sleep through a single night. These planets are heated to thousands of degrees on their sun-facing sides, causing rock to vaporize and form atmospheres composed of mineral gases. Their skies might shimmer with clouds made of silicate particles, and metal could condense and rain down as droplets of molten iron. Intense radiation strips these atmospheres away continuously, leaving long, comet-like tails of escaping gas trailing behind the planet as it hurtles around its star. The gravitational pull is so overwhelming that many are tidally locked, with one hemisphere forever exposed to stellar fire and the other cast in eternal shadow. Their blistering orbits carry them through warped spacetime at incredible speeds, illustrating the sheer range of planetary environments that can exist when nature tests the laws of physics to their most dramatic extremes. Among the vast catalog of exoplanets, some are so puffy and lightweight that they would theoretically float in water if such an ocean existed on a cosmic scale. These planets have extremely low densities, often less than quark, due to their giant sizes combined with bloated atmospheres filled mostly with hydrogen and helium. They are known as superpuffs, or cotton candy planets, orbiting close to their stars where stellar heat expands their gaseous envelopes to enormous volumes. Despite their impressive radii, their total mass might only equal a few Earths, making them incredibly fragile and delicate. The slightest increase in stellar radiation, or a close encounter with another massive object, could strip away their atmospheres completely, reducing them to tiny cores. This strange state challenges our understanding of how planets form, suggesting these worlds either accumulated gas very slowly in gentle environments, or formed quickly with vast frozen cores before drifting inward. Their existence shows how delicately balanced a planet can be, surviving only because the universe allows it a rare and narrow set of perfect circumstances. Jupiter is the heavyweight champion of our solar system, but other systems contain planets that make it look modest by comparison. These super-Jupiters can be 10 or even 20 times more massive, yet still qualify as planets because they are not quite large enough to ignite nuclear fusion and become stars themselves. Their immense gravity can dominate entire systems, steering the orbits of neighboring planets, sculpting debris belts with invisible hands, and even preventing smaller worlds from forming at all. Their atmospheres may be crushingly dense, filled with exotic chemistry driven by immense internal pressures and heat left over from formation. Some of these giants orbit close to their stars, becoming scorching hot and glowing faintly in infrared wavelengths, while others roam far out in the frozen dark with cloud tops colder than any temperature recorded on Earth. The scale of these worlds stretches the very word planet to its limit, showing that even within a single category, the universe permits extraordinary diversity and refuses to be bound by our expectations. While our Earth orbits a single star, some planets follow paths around multiple suns, circling them as a unified group. These circumbinary or circummultiple worlds experience a complex gravitational ballet where the star system itself twists, turns, and wobbles as the planet maintains a wide, stable orbit around the center of mass. The skies of such worlds might feature 2 or 3 sunrises and sunsets each day, their positions shifting over time as the stars interact and dance around one another. Temperatures on the surface rise and fall in strange, unpredictable cycles defined not only by distance to the stars, but by the shifting influence of multiple companions pulling in different directions. These planets survived the chaotic birth, where the turbulence of multi-star formation could have easily ejected them into the void. Instead, they found balance, circling a gravitational center that itself drifts through the cosmos like a living, breathing system. These worlds show that stability is still possible even in what appears to be chaos, and that the universe's rules always find ways to carve harmony from complexity. Star clusters are dense neighborhoods where thousands of stars form together in a single burst of creation, packed so tightly that the night sky on any planet would glow with countless nearby suns. For a long time, astronomers wondered if planets could even survive in such busy environments where passing stars might strip them away or disrupt their delicate orbits. Yet observations have revealed planets nestled within these stellar cities, orbiting their parent stars in relative peace despite the crowding. These planets may experience close encounters with other stars every few million years, events that might subtly change their climates or shift their positions slightly, but many endure for billions of years regardless. Their existence suggests that planetary formation is remarkably robust, capable of unfolding even in crowded nurseries where radiation, gravity, and motion collide constantly. To stand on such a world would be to witness a sky that never grows truly dark, where the cosmos blazes with perpetual starlight, and planetary life shares space with the furnace glow of young neighboring suns. Stars travel through the galaxy like ships crossing a vast ocean, and sometimes their paths bring them dangerously close to one another. When a passing star swings near a solar system, its gravity can tug on planets, asteroids, and comets, reshuffling or even ejecting them into interstellar space. This kind of disturbance may send icy bodies plunging inward to bombard inner planets with water and organics, or pull distant worlds into new orbits that dramatically change their climates. Some planets might be completely lost, slung into the void to become rogue wanderers with no sun to call home. These encounters are rare on human timescales, but practically guaranteed over the lifetimes of stars, which span billions of years. The fossil record of such an event may be seen in oddly tilted or highly eccentric orbits, subtle hints that something violent happened long ago. Disruptions remind us that solar systems are not isolated islands drifting alone, but travelers in a dynamic, interconnected galaxy shaped constantly by encounters we cannot yet see, but can infer from the patterns left behind. When a star dies gently, shedding its outer layers to become a quiet white dwarf, it sometimes leaves behind a swirling disk of gas, dust, and shattered remains of earlier planets. Within this disk, new planets can begin to form, recycling the materials of a previous generation into fresh worlds. These second-chance planets may contain elements forged in the heart of the dying star, giving them unusual chemistry or dense metallic cores unlike anything in younger systems. Their parent star no longer burns with the fury of youth, but glows faintly with leftover heat, casting dim light across landscapes that might still hold warmth deep underground from radioactive decay. The idea that planets can be born from the ashes of their predecessors expands the life cycle of solar systems beautifully, proving that destruction can also be a kind of creation. These reborn worlds occupy a twilight realm of astrophysics, where the end of one cosmic story becomes the prologue to another, where death and birth are not opposites, but partners in an eternal dance. When two enormous clouds of gas drift through a galaxy and intersect with enough force, they can trigger waves of star formation. The collision compresses hydrogen, helium, and interstellar dust, causing pockets within the clouds to collapse under their own gravity. These compressed pockets become cradles of new stars, each potentially surrounded by disks where planets may emerge. This dramatic beginning leaves fingerprints in the systems that form. Initial turbulence can result in planets with wildly tilted orbits, unusual spacing, or unexpected chemical makeups. Some planets may form quickly and grow massive before the chaos settles, while others emerge later from leftover debris that finally finds peace. Even the stars themselves might be born as siblings, traveling through space together for millions of years, each with its own family of worlds. This kind of cosmic collision shows that star and planet formation is not always a calm, orderly process. Sometimes it begins with an interstellar impact that violently sets the stage for entire families of worlds to be born from chaos. Not every protoplanetary disk coalesces into solid worlds. In some solar systems, dust and gas remain in suspended swirl for billions of years, never fully gathering into planets. These glowing, translucent clouds reflect starlight and reveal a stalled process of planetary birth. Perhaps the disk lacked enough mass, or early disturbances prevented larger bodies from forming. In other cases, unseen planets may lurk within, shepherding the dust into rings and lanes without ever clearing a complete path. These half-formed systems act like time capsules, preserving the raw ingredients of planet making long after neighboring systems have moved on to develop rocky surfaces and stormy atmospheres. They also replenish the galaxy, slowly sending dust back into interstellar space where it might one day seed the next generation of stars and worlds. Studying these lingering clouds helps scientists understand the delicate balance required for planets to emerge and why some stars never end up with fully formed worlds at all. In the vast outskirts of certain solar systems lurk planets so distant that their host star appears merely as a bright speck in the sky, no larger than Venus appears from Earth. These worlds move through regions where warmth from the star scarcely reaches, plunging their surfaces into bitter, unrelenting cold. Any atmosphere they retain may freeze into layers of ice stacking over centuries until only the thinnest slivers of gas remain aloft. Yet some of these distant giants may harbor internal heat from radioactive decay or the lingering energy of their formation, creating subsurface oceans beneath kilometers of frozen crust. Their slow, monumental orbits can take thousands of Earth years to complete, making their seasons longer than the entire recorded history of human civilization. These remote worlds remind us that the architecture of a solar system can stretch far beyond the cozy zones where warmth and light create familiar landscapes. In those distant, shadowy reaches, alien chemistry and sheer endurance replace sunlight as the ruling forces of planetary existence. Across the galaxy, planets display an astonishing variety of extreme environments, shaped by their atmospheres, rotations, chemistry, and the nature of their parent stars. Some worlds experience gemstone storms, with silicate crystals raining from violent skies. Others are tidally locked, split between eternal day and endless night, creating unusual climates along the twilight zone. Rapidly spinning planets become distorted by centrifugal force, developing intense weather and unstable shapes. Highly reflective worlds shine brightly due to mineral clouds or molten surfaces, while rogue planets wander alone without stars, lit only by their internal heat. Exotic matter planets may form under extraordinary pressures, producing diamond mantles or metallic hydrogen interiors. Some stars show traces of engulfed planets, revealing the dramatic end of those worlds. Giant planets with powerful magnetic fields create massive auroras, while multi-belt systems preserve the history of planetary formation. Small red stars host long-lived planetary systems, and many close-orbiting worlds lose their atmospheres to intense stellar radiation, leaving behind bare, rocky remnants. Some planets shed gas tails like comets, others survive in the shadows of massive stars, and a few orbit black holes where gravity dominates everything. Luminous young planets glow with internal heat. Dusty systems remain turbulent for millions of years, and interstellar planets can migrate between stars. A number of giant planets even form in sudden gravitational collapses rather than slow accretion. Together, these worlds reveal that planets are far more diverse and dynamic than our solar system alone suggests. From blazing atmospheres to frozen darkness, from gemstone storms to diamond interiors, the cosmos constantly reshapes matter into forms both violent and beautiful. This diversity shows that planetary systems evolve through chaos, chance, and extreme physics, reminding us that the universe is filled with possibilities far beyond anything we once imagined.